Okay, so good afternoon or good morning, depending where you are. Thank you very much for being here today again. So I have the great pleasure today to present Professor Cynthia Rudin. So we have known each other for a while, and she's actually the scientific leader of Duke University at our project NEED. And Cynthia is basically scientific, well-known leader around interpretable machine learning. This was one of the reasons why she was elected in 2019 fellow of the American Statistical Society. And when you see her work on interpretable machine learning, you will see that she has applied this to different fields, including energy, criminology, etc., healthcare also. So for me, it's a great pleasure that she is joining us today. It's not easy, as we know. We have the time difference, we have the homeschooling and many other things, but when we invited her, she was immediately positive about it. So it's a great pleasure to have you here, Cynthia.
Thank you, Dolores. Let me share here. Awesome. Okay, can you see my screen?
Yes, we do.
Yes.
Oh,
So much.
great. Excellent. Okay, so I'm going to talk about decision tree optimization today. So I want to start with just a little bit of background on interpretability. So I just want to ask a question. Can typographical error lead to years of extra prison time? How could that possibly happen, right? That is not the way any criminal justice system is supposed to work. But it actually did happen, and it happens all the time. Okay, so this is the case of Glenn Rodriguez. This is a New York Times article, and it talks about this man, Glenn, he was in prison for many years from a crime that he committed as a child, and he was denied parole because his COMPAS score was miscalculated. Now, COMPAS is a predictive model that's widely used in the U.S. criminal justice system, and it has up to 137 factors in it. Like there's a score sheet that's computed, and he compared his after his parole was denied, he compared his score sheet to someone else's, and he noticed a typo in his criminal history features. So typographical error actually made this mistake. And so we were thinking that, these black box models used in the justice system, they've got to be really accurate in order to justify the complexity of them and the black boxiness of them. And so we got some data from Florida, and we were able to try to examine how accurate COMPAS was. Okay, so we took the data from COMPAS. This is a very famous data set from Florida, where they provided COMPAS scores and a few features about each person. And we took that data and, this is not all of the 137 factors. This is just a few factors. And then we took those factors and built a predictive model for recidivism prediction, for prediction of arrest within 2 years, using our latest machine learning method at the time, which was called corals, or certifiably optimal rule lists. So anyway, so we pitted corals against COMPAS, and we fed all the Florida data into corals, and it gave us a machine learning model that was so tiny that it fit in the bottom of a PowerPoint slide. And the model looks like this. It says, if you're young and male, predict you'll be arrested within 2 years of your COMPAS score calculation. Also, if you're a little older and you have a few prior offenses, predict arrest within 2 years. Or if you have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this and we were like, there is no way that this model can be as accurate as COMPAS. No way. It's just so tiny. But we were wrong. As it turns out, COMPAS and that corals model I showed you are about equally accurate. And this is across 10 folds of cross-validation. So each color here is a different fold of the data set. And not only were COMPAS and corals equally accurate, we also tried a whole lot of different machine learning methods, like the whole arsenal of machine learning methods, and they all performed the same. And that includes things like boosted decision trees, which are so complicated that you can't put them on a PowerPoint slide. support vector machines with radial basis functions, random forests, and so on and so forth. So you have these, like, a bunch of these models are black box models, and then compared to a model like Coral's, the whole model is on the screen right there in the corner. So anyway, there was this huge debate about algorithmic fairness of COMPAS, of this model. But the truth is we just don't seem to need COMPAS at all. So why are we still using it, right? Now, what I'm showing you here, it exemplifies a much larger phenomenon, right? It's not just this data set where everything performs the same. There are many, many data sets where you see essentially the same performance across many different algorithms. So let me talk about that a little bit. There's really two kind of major types of data. There's tabular data and raw data. In tabular data, all the features are interpretable, and this like tabular data problems include lots of problems in criminal justice and healthcare and social sciences. And basically, this is the kind of data that I always end up getting. I don't know why, but like every time I work on a problem, somebody hands me data that looks like this. And then on the other end of the spectrum are raw data problems where it's like images or sound waves or large bodies of text where each individual pixel is not really meaningful as a feature. And for these kinds of raw data problems, like neural networks are really the only type of method that's working right now. Whereas for tabular data, with minor preprocessing, all the methods have similar performance, including neural networks, and you're getting very similar performance across algorithms. So what I showed you with the COMPAS data, that happens very, very, very often. And so that opens up an opportunity to design very sparse models that are equally accurate to the best model that you can construct. Okay, so this really opens up major opportunities when you're working with this type of data to try to construct simple models like the Corals model that I just showed you that doesn't lose accuracy over a black box, but it's really interpretable. And so I want to talk about sparse decision trees in this talk, just like the Corals model is a very sparse decision tree. Now, decision tree algorithms have been popular since the very beginning of machine learning. And the main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been greedy, like myopic algorithms that construct trees from the top down, like C4.5 and CART. And the problem with these, using a greedy algorithm is that if it chooses the wrong split at the top of the tree, there's no way to undo it. You're stuck with it. And so a lot of these algorithms spend a lot of extra splits undoing mistakes that they made at the top. But it's really hard to improve over the greedy methods because decision tree optimization is really hard, both theoretically and practically. There's a combinatorial explosion in the number of possible trees that we could consider. Yeah, so it's NP hard, it's factorial in the number of variables. These are hard problems. So for a long time, people just didn't even try to do anything except really, greedy methods. The greedy methods was king. So for greedy methods, what people do is, as they construct from the top down, they create splitting conditions and pruning conditions based on statistical hypothesis testing. So you split, and then you look at this subset of the data, and you say, okay, I could split on all these things. I'll do a statistical test and figure out how to split. So it's not a global criteria, it's just a local criteria. And then after the tree was constructed, they again do hypothesis testing to figure out how to prune. So they might look at a subtree and say, oh, okay, my statistical test says that I should prune this to a leaf, and then they would go ahead and do that. Now, just to give you a little history of decision tree optimization, this is a very old field. It started at the beginning of machine learning, essentially, and then it gets to sort of popular players like CART and C4.5. And then from there, the field split into at least 4 pieces. The first one combined trees into form ensemble models, but ensemble models are not interpretable. And then there were 3 different other branches, at least. One is sort of global optimization of trees. So immediately the optimization people said, there's an opportunity here. We should really try to fully optimize these trees. And then the statisticians were really working on this branch. They were trying to figure out what are the best hypothesis tests for splitting and pruning. Whereas, oh, and I should say, by the way, there are tutorials on this, but you should really be careful of them because they don't include any of the work from the optimization side of things. And then there was another branch of statisticians that were trying to use decision trees to solve other types of problems besides classification, trying to do longitudinal data analysis or build survival curves, things like that. So what I hope is just, oh, sorry, before that, the people working in, the statisticians working in this area here, they noticed problems with, they had identified problems with their approaches. And specifically, they noticed that sometimes trees choose irrelevant variables. And they noticed that the trees don't perform very well compared to ensembles. And they couldn't tell how close to optimality their trees actually were because of everything, all the decisions were made were all local. And they also needed new splitting criteria for every single objective they wanted to optimize. So for example, Cardency 4.5, their splitting criteria is really great for just classification accuracy, but not for really anything else. Like if you wanted to optimize for area under the curve or something like that, you couldn't really do it without inventing new splitting criteria. So what I hope is that the tools that were developed, extended from the optimization literature can actually really help with the problems that the statisticians have identified. So let's consider the possibility of fully optimal decision trees. The user picks the objective, whatever they want, AUC, or weighted misclassification error, whatever they want, partial AUC. And then the trees are then regularized for sparsity to make them interpretable, to make them nice and sparse. Okay, so then in that case, the issues that the statisticians figured out kind of go away, like the fact that trees choose irrelevant variables. They wouldn't be choosing irrelevant variables anymore because the trees are fully optimized. And they wouldn't be worse than ensembles necessarily because, they're fully optimized. And you could tell exactly how close to optimality they were because you get an optimality gap if you couldn't solve full optimality. And you don't need any splitting criteria at all because you're not doing splitting and pruning, you're globally optimizing. And so this is the direction that I'm really going to talk a lot about today because I think this is really important because it can solve really, I think, all the problems that the statisticians were identifying in the future. So we could take these approaches and try to help adjust them to try to handle the other issues that the statisticians have identified. Although this work hasn't been done yet, this is sort of in the future what I hope will happen. So I'm hoping if we pursue this agenda, then we could actually solve all of these problems. Okay, now there have been several approaches for doing this. I'm just going to overview those approaches. So there's people doing genetic programming and neural networks. The problem with these methods is, again, it's just heuristics, and you don't get really a notion of how close you are to optimality. You don't really know whether your modeling choices were bad or your optimization choices were bad. And that's really problematic in practice because you can't fix the problem once you know you have it. And then there's some work using SAT solvers, which I think is really novel and innovative, except for the fact that it only works on data that it can be perfectly separated. And I don't know any real data sets like that, although this work could potentially be adapted, but I'm not sure how. And then mathematical programming solvers have been used since the beginning of, since the 1990s, and they've been quite successful. They're very flexible too, which is great. I'm very familiar with BinOct, which is a very, very good method, and we've been comparing a lot with that one, as I'll show you later. But I think this type of approach is really promising, as well as the works that do dynamic programming with branch and bound. So these are approaches that do dynamic programming but have bounds in the middle of them. And this is the approach that we've been pursuing, as well as DL 8.5, which is kind of, these two algorithms I think are the leaders, at least of 6 months ago when we did our latest set of experiments. So I'm going to talk about our work, which is called GHOST. Ghost is about 3 orders of magnitude faster than the other methods for solving these types of problems. And so I'm going to tell you about how it works. Now, I should mention that the field is moving very, very fast, and there have been a number of papers published in the last 6 months that we haven't yet been able to compare with. Okay, so let me go over what Ghost does. So Ghost is an optimization method, and this is the type of objective it optimizes. So it's trying to minimize a function, an objective, over all possible trees, binary trees, where it's trying to minimize a combination of misclassification error and sparsity, and then C is the trade-off parameter that governs the trade-off between the predictive performance and the sparsity. So if you solve this to optimality, you get a tree. So here's an example of an optimal tree on that Florida rearrest data that I was showing you earlier. So you solve a problem like this, and the solution is something that looks like that. Okay, so now I want to tell you a little bit about how dynamic programming and with branch and bound actually works. So you start with a full data set and a naive label. So here there's 2 classes, blue and yellow, and everything is predicted to be blue. It's all in one leaf. And then you create every possible size 1 tree. So single split tree, okay? Sorry, size 2, I guess, because you're splitting. So you now have 2 leaves. So you split, you do every possible split. And here I've only listed 3 of them. But the truth is that there would be quite a lot of them, but I just don't have room on the slide to list quite that many. So then from there, you create every possible tree with two splits or 3 splits, right? You literally just enumerate the whole search space. So here we go again. You continue to split. And so as you can see, the search space is growing very, very quickly. This is an enormous, enormous search space. But it's not as big as you might think. And some of the problems are easier than you might think. Here's how. First of all, if you have a pure leaf, you wouldn't split it anymore. That subproblem is done. If all the points in there are classified the same way, there's no reason to split it. And then the other thing is that if, in different branches of this giant problem space, let's say you encounter the same subproblem. So in other words, these data points are the same as those data points. So if you solve this subproblem once, you can actually take the solution and feed it in everywhere you see that subproblem. So these are actually duplicated subproblems. Solve it once, and that subproblem is done. So in the approach of Ghost, it relies heavily on consolidation of duplicated subproblems. Okay, so now let me one of the issues with these big optimization problems is you run out of room on the slide very quickly. So I'm going to expand outward this time. So I'm going to just expand my search space out like this. So let's say that you start doing this. You start creating this large search space, enumerating all of the subproblems. And then after you've finished, you've solved all of the subproblems. And then at that point, you can put all the solutions together and form an optimal tree out of it. So our goal is to solve all of the subproblems optimally using this dynamic programming approach, and then put together the optimal tree in the end. Okay, another thing that really helps us is the fact that certain subproblems can be proven to yield non-optimal solutions. So let me kind of show you a little bit more about that. So what we're doing is using theorems to try to reduce the size of the search space. So we have all these analytical bounds, and they literally lop off big chunks of the search space so that the part of the space we actually have to search is much, much, much smaller than you might think. Okay, so so I'm going to, let's say I'm building my tree, okay? So I'm in some part of the search space. Now what I'm going to do is I'm going to not touch these leaves for now. And maybe in a different part of the search space, I can touch those leaves. But for now, I'm going to say that these leaves are designated as fixed leaves. And these leaves are allowed to be extended. Okay, so I can calculate the loss in the leaves that are fixed because that is not going to change as I continue growing this tree. So my objective looks like this. As you know, it's a sum over the sum of it should be a sum over the points, and then sorry, one over the number of points, and then the sum over leaves, and then the loss of each leaf. So for instance, over here, I lose 8 points for this leaf. I lose 15 points for that leaf. Okay. So then I can split this loss into two pieces. One loss for the fixed leaves where I know what the computation is, and then another for the unfixed leaves where I don't know what's going to happen because I haven't made those splits yet. Now, what I'm going to do is create a lower bound for my objective by saying that the best possible loss on the unfixed leaves is 0. The loss is always non-negative, and so a lower bound is constructed by setting this to 0. And this lower bound right here, I call it B. This is my hammer that I'm going to use to reduce the size of the search space. Okay, so again, my lower bound is the objective, but I remove the term for the leaves that haven't been constructed yet. Okay, all of these guys, the loss is optimistically set to 0. All right, so let's say that during my computation, I have encountered a tree that is my best so far that has a loss that looks like this. Like it has only 3 leaves, and I've only lost 12 points. So in that case, let's say that this best so far tree is actually better than my lower bound for my current tree. In that case, that helps me because it means that there's nothing I can do to extend this tree to form an optimal full tree. Okay, so if I can get that inequality to hold, then I can eliminate the tree and all of its children from the search space. Okay, so we know that this is less than my current tree, so I know that my best so far is always going to be better than the current tree and any of its children. So this is called, so this tree and any of its children will never be as good as the current best. And this is called the hierarchical objective lower bound. And again, this is our main tool for reducing the size of the search space. So the hierarchical objective lower bound says if the best so far is better than my lower bound for the current tree I'm working on, then this tree and all its children can be eliminated from the search space. Okay, so there are variations on this bound that make it more powerful. Let me talk about the hierarchical objective lower bound with a one-step look ahead. So let's say that I'm doing my computation and my current tree has its lower bound. I add one value. I'm going to pretend that I add 1 leaf to the tree. So this is just, if I add 1 leaf, I add 1 regularization parameter to both sides. Okay, I can do that. I can add anything to both sides that I want. But this is the same thing as if I sort of made the tree 1 child bigger, 1 leaf bigger. So let's say that I'm still all right, like my lower bound is still better than the current best. So technically I could still extend this tree to be the optimal tree. However, it's close. And it's close to the point that if I add even 1 more child to my tree, then I do worse than the best I've seen so far. So yeah, so this is less than the objective of my tree with at least 1 child. And so I know that if I add anything to this tree, I'm done for. Like there's no way that it can be extended to form an optimal tree. So yeah, if I even add 1 child to my tree, it's going to be worse than the current best that I've seen so far. And then that means I can eliminate all of the children from consideration in the search space. And so this is called the hierarchical objective lower bound with the one-step look ahead. So if the best so far is less than the lower bound for my current tree plus 1 regularization parameter, then all of the trees, child trees, are suboptimal. Great. So chop off parts of the search space. Just hack them off. Okay. So then there's also a version of the hierarchical objective lower bound for subtrees. So let's say that, you know, so we again have our lower bound, again eliminating all of the terms that come from the parts of the tree I haven't constructed yet. I can split it into a left and a right, and I can do that however I want. Like I can make this the left, I can make this the right, I can make this the left, I can make that the right. However I do it, I can just split up the nodes into left and right. And if this bound is violated on either the left or the right, then I can eliminate the whole tree and all of its children. So if either side is bad, the whole tree is bad. And that's true even if the other side hasn't been constructed yet, which is great because it means I don't even have to construct that side. I've already proven it's bad. Okay, so this is the hierarchical objective lower bound for subtrees. If the left tree is bad, subtree is bad, or the right subtree is bad, then you can eliminate everything. Okay, so there's several other bounds here. So one of them is very powerful, which is called the leaf bound. And the leaf bound says that the maximum number of leaves of any optimal child tree. So in other words, you have a partial tree here, and you're trying to extend it into an optimal tree. So if your child tree is going to be optimal, then the maximum number of leaves it has is upper bounded by this equation here, which is the number of leaves of your current tree, which is 2 right now, plus the, it's 4, 1, 2, 3, 4, because we haven't extended it yet. Okay, so it's 4, plus this term right here, which is the best so far that we've, the objective of the best tree that we've seen so far, minus the lower bound for our current tree, divided by the regularization parameter. And so this bound is nice because it tells you, as you're constructing the tree, how many leaves you can afford to have before the tree can be provably suboptimal. So it really tells you that your search space is much more limited than you might think. Like you're not going to search for really, really big trees. That's not going to happen. Okay, so then there's another bound, which is also a really excellent hammer on this against this problem, which is the equivalent points bound. Now the equivalent points bound says that if you have a collection of points that are exactly on top of each other, but they have different labels, then there is no way that you can classify all of these points correctly. So here I have 5 points that are identical to each other. 2 of them are positive and 3 of them are negative. And so that means you can't get them all right. Like you have to miss at least 2 of them. And so we're going to have to miss, the minority of them. I could miss 3 or I could miss 2, but I have to miss at least 2. Okay, so the equivalent points bound says that equivalent points with differing labels cannot all be classified correctly. The minority in each equivalence group must be misclassified. So at least that minority must be misclassified. Okay, and then there are other bounds too, which are things like the incremental progress bound, which is at least, so each split must provide a reduction in loss of at least C, because C is the regularization parameter, because if that's not true, you can prove that that split should have never happened. And there are many other bounds which I don't want to get into, but I hope this gives you really a flavor of the type of approach that we're trying to take toward this problem. Now, my collaborator in this is an expert in computer systems, and she has been so amazing in helping us speed up this code with some really innovative data structures, and we've really co-designed the algorithm with the data structures that we're using. So one interesting thing that we're doing right now is we're representing each subproblem by its contents. So in other words, a subproblem is represented by the data points that fit into that subproblem. So normally you'd think about representing a tree like this, like what I have on the right here, but that's not how we represent a tree in our database. We represent it as a series of bit vectors that tell you which data points fall into which leaf, right? So for example, in the first leaf, this rain and construction leaf, then that's the points that are over here. So you can see that the first data point and the 6th data point, 5th data point? No, I can't tell. 6th data point are both in the first leaf. And they're both in the same subproblem. Whereas in this leaf over here, that includes the second and third data point, and so on and so forth. So the fact that we can, you know, represent the subproblems as bit vectors allows us to make the computation really, really, really fast. Okay. We also have something called a permutation map that keeps track of identical trees that have already been evaluated. So if you take this tree and you rearrange the leaves, you have an equivalent tree, and you don't need to, you know, work on these two trees separately because they're actually like equivalent to each other. So we have a data structure that keeps track of all the trees we've looked at so far. So every time we encounter a new tree, we go back and look it up to see whether we have already worked on that problem before. And if we have, we don't need to do it again. Okay, so Ghost has the combination of dynamic programming to search through this space, but bounding it with these strong analytical bounds that reduce the size of the space, representing each subproblem as a bit vector, which makes and having this special fast bit vector library to make all of our computations really, really fast. The consolidation of repeated subproblems so that we're not redoing computation over and over again, as well as the permutation map that makes sure that we can look up every tree that we've processed so far, every partial tree that we've processed so far, so that we don't, again, repeat computing the same thing over and over again. This really leads to much, much, much faster computation than we have really seen in other approaches. Now, Ghost is actually much more general than I've sort of discussed so far. Ghost actually can handle a variety of different loss functions. It can handle any loss function that is monotonically increasing in the number of false positives and false negatives. Now, I don't know why anyone would want to create a loss function that doesn't increase in the number of errors. And so this is actually very, very general. It includes things like balanced accuracy, weighted accuracy, F1 score, precision, anything else that you really can think of that's like a normal loss function in machine learning. It also can handle rank statistics, like the area under the ROC curve, and also the partial area under the ROC convex hull, things like that. However, you do lose some of the theorems because some of the analytical bounds rely on additive loss functions. So the algorithm performs more slowly when you use rank statistics. But when you do use different loss functions, you actually do get different results. So I'm showing you here a result on the Florida data set from Ghost optimized for accuracy. But I could also change the objective function and do a balanced accuracy or in the AUC convex hull, and I get actually different trees. Now, the main experimental results, I don't want to go into I don't want to show you slide after slide of experiments. I'll just show you a few. But the main results from the paper are that we have similar classification accuracy to black box methods, which makes sense because that's true for sort of all tabular data problems. So that's not really a surprise. What really is there are other surprises in here. A nice thing also about Ghost is that for custom losses, like if you have your own custom loss that you care about and you want to plug it in, you're actually going to be much better than the greedy methods like CARD and C4.5, because those methods are, like I said, their splitting criteria was optimized in the 80s and 90s for classification accuracy. And so those methods just have trouble adapting when it comes to other loss functions. And the trees that we're getting, of course, are sparser than all of the heuristic methods because we're actually optimizing for sparsity. So that's not a surprise. But the big surprise is that we're orders of magnitude faster than the next best method, or at least we were 6 months ago. So let me show you some experiments that are really the main result here, which are scalability experiments. So this is on the FICO dataset, which is the dataset from the Explainable Machine Learning Challenge in 2018, and the goal was to predict whether someone would repay their loan. Okay, so here, what I'm showing you is number of features versus runtime. Unfortunately, we couldn't include binoct because it was just too slow, but I don't want you to think that this is a bad method. Binoct is actually really, like I said, it's a very, very good method, very flexible, and I think it really has potential to get up to this speed. So I don't want you to think that I'm sort of knocking it in that sense. But the generic mathematical programming solvers just have a hard time competing against these sort of custom design methods for solving these problems. So this is DL 8.5. This is just another method in a similar vein to our method. This is the Python version of Ghost, which really shows you the slowdown due to using Python rather than our custom bit vector libraries and so on in C. And then this is our method from last year, which is OSDT, Optimal Sparse Decision Trees, which also a similar approach, but had much less of the sophistication that Ghost does. Ghost is in blue over here. It does go up, right? It does, at some point you do hit that very, very fast or very, very bad slowdown when you get to a large number of features, but the whole goal is to get that slowdown to be later on so that we can do more and more features and do practical problems. So here it occurred after we had over 100 features, which we're proud of. And then the yellow here is CART, which is very fast, but produces very suboptimal solutions. Okay, yeah, so the improvement is in orders of magnitude. So that's what's really great about working on this problem, is that you're rewarded in orders of magnitude and speed up. And this is for the Florida Compass data set. And again, the results are very, very similar to the previous slide. So DL 8.5, the Python version of Ghost, OSDT, Ghost here. It does again slow down here after 120 some features. And then this is CART, which again is suboptimal. Now, in terms of the flexibility, this is some results on the 4-class data set. So if you use different types of objectives, balanced accuracy, weighted accuracy, F1 score, AUC, partial AUC, you're going to get different results on the training set. And then because these models are so sparse, those results tend to carry over directly to the test set. And then here are just some of the different trees showing you that you actually do get different trees when you optimize different objectives. I think I'm going to maybe skip this one, but this is showing you scalability in the sample size. And there are some interesting results here, but like for instance, this one I thought was really interesting, where as the number of samples increases, the runtime kind of gets longer and then gets shorter. And I think this is because the problem actually gets harder when you have fewer samples, because there's more uncertainty in what splits are allowed and what are not. And when you have more data, the bounds kick in and just say, nope, not going to split here. And then the runtime can be faster again. Okay, so just some notes. I want to point out that different methods solve different problems. So if you want to compare like the Ghost algorithm to DL 8.5, it's actually not that easy. These algorithms actually all solve different problems. So the literature is actually pretty confusing, and we have spent a long time trying to sort it out. So for instance, Ghost is solving this problem over here, where it's like regularized loss, where the optimal tree can be any size, whereas other algorithms solve different problems. Like they say, like binoct, for instance. Binoct solves this problem. It says, find me the minimum loss tree such that the depth of the tree is some number. Now the issue with this is that you have to know in advance what the depth is, and then binoct creates a complete binary tree of depth, whatever it is. So even if there's a sparser tree with or a lower depth tree, binoct might not find it because it's going to use a full binary tree of that depth. And so the problem on the left there is much, much, much harder, because it's assuming that you can look through the entire space of trees, whereas the algorithm over here is only looking at a very specific subset of trees, right? So it's really hard to tell which algorithm is better, because if you want to solve this problem, this algorithm is going to take longer because it's looking through a much, much bigger search space. So a lot of people have had trouble kind of directly doing that comparison. And one paper tried to handicap Ghost by removing the regularization term. But the regularization term is where all of the bounds come from. And so by doing that, it actually wrecked Ghost's scalability performance. So you got to be careful when comparing these algorithms. Also, when you look at different papers, the pre-processing that they're doing on the data is actually different for different problems, or different papers, I'm sorry. So for example, DL 8.5 and I think one of the other papers uses what's called bucketization, which actually sacrifices optimality. So you have to kind of be careful about looking at the scalability numbers there. And then another thing we found is that code wasn't always publicly available for some of these methods. Our code is. And so is DL 8.5, and so is binoct, which allowed us to do the comparison to them. Okay, so just to summarize, I'll summarize in one sentence. Modern decision tree methods are just not your old cart. Thank you.
Thank you very much, Cynthia. It's been a very nice talk. Are you okay if we open the floor for questions?
Yes, let me just figure out how to stop sharing.
Yeah.
There we go. Okay, great.
Yes, then we see you better. Okay. Yes, so what we have normally done is that either you raise your hand or you can put in the chat. I'm fine either way. Yeah. So is there any question from the audience? Yes, we have a hand from Juan Pablo. Yeah. So would you like to, state your question?
Hi, yes. Hi, Cynthia. Amazing presentation. The lies very completely. I had a question about the percent of the data that you had for making the training and the test, because you know most more of the problem in this subject, you need a good percent of data available to making the process. There are so influence of the available data for the performance of your methodology.
I'm not understanding the question. I'm sorry. So where are you using data sets that are publicly available?
Of course. When you try to work in perhaps and SVM, you had a balanced data, and you had a good percent for data available. If you have a little percent of the data available, maybe the 10%, that can be that can be give you a bad performance or your methodology in order to classify the problem.
Yeah. Oh, okay. Yeah. So you're talking about imbalanced data. Yeah.
Exactly.
So luckily we allow customized objectives. And so if you have an imbalanced data problem, you can put in your own objective. You can do a balanced accuracy or a weighted accuracy to try to boost the importance of the minority class so that you can actually perform well. And actually that's the reason why we made Ghost so general, was because we were having trouble with imbalanced data.
Yeah.
Okay.
Thank you so much. Yeah. Thank you, Juan Pablo, and thank you for the answer, Cynthia. I see another hand, Marcin. Would you like to state your question?
Yes, sure. Hi, I'm Marcin. I'm from Poland, and I have one question regarding to the interpretable models, because my question is that have you tried this on like real data and checked how more sparse results you're obtaining than, for example, the solutions from the random forests or something like this? I know that there is the method built in which is reducing the number of features, but I do understand that this method gives you the opportunity. And the question is whether you try it and it showed that in fact you are reducing this level of complexity. And another thing related to that, I mean, once you mentioned that there is like 100 features, do you really, I mean, take such a decision tree with 100 features as an interpretable algorithm?
Yeah, so those are really good questions. Let me try to answer all of them. The first one, we do have an extensive set of papers in the experiments in the paper that compare the accuracy of our methods to, random forest and boosted decision trees, and all the methods tend to perform the same, which is something we found for years and years and years over lots of different, problems and algorithms. So that's really not a surprise to us. It's almost like, we have the same piece of code and we run the same algorithms for all these different data sets, and they're always, producing essentially the same thing. And this should not be a surprise to anybody working in machine learning, because this is, people were claiming we were overfitting the UCI repository because, all the methods just tend to perform the same. So yeah, so that's not a surprise. And then the other question you asked was also really good. Sorry, remind me what the other one was?
About the size of the tree, whether it's interpretable.
Yeah, right. So that 100 features is not the size of the tree. That's the size of the input.
Okay.
Yeah, the size of the tree is much, much smaller. They're tiny. And in fact, it just depends on what value you put for the regularization parameter.
Okay. Yeah, because I'm asking because from my experience, a lot of people are saying that, like, their logistic regression or the decision tree is interpretable, and they are performing such a big feature engineering and so complex features into the model that in fact it's very difficult to understand what is going on and how the model was built. And regarding to that, once I heard this 100 features, I had the feeling that even though I have a potentially algorithm that it's easy to follow, to build the interpretation based on that, it might be tricky, but you gave me the answer. Thank you very much for your answer.
Yeah, no, the trees are usually like maybe, at the most 10, I would say. Yeah, they're really, really tiny. Yeah.
Thank you very much for the answer.
Thank you very much for the question, Marcin, and thank you very much for the answer, Cynthia. So we have Ilke, who has also raised the hand. So Ilke, would you like to put forward your question?
Yeah, sure. I'm just trying to be visible. Do you see me? It's just, hi, Cynthia. Very, very nice presentation. Thanks a lot. My question is about whether you have experienced that you had multiple solutions, because now you're talking about an optimal solution, which I can imagine, because with the dynamic programming, you're obtaining an optimal solution. But the thing is, do you think that there are many solutions which will really give you the same objective function value? Because the trees could be quite different. Do you have any experience with that?
Yeah. So this is actually this is an excellent question. So actually we just wrote a paper about this. So the notion that there are multiple good solutions, multiple equally good solutions, I believe is the reason why we can even find trees that are as good as, say, a random forest or something like that. So we call this the Rashomon set. So the Rashomon set is the set of approximately equally good models, leveraging sort of Breiman's language of Rashomon, the Rashomon phenomenon, or whatever he called it. But essentially, yes, there could be a huge number of slightly suboptimal trees. And I think figuring out how to explore that space is an important open problem. So we just published a paper in Nature Machine Intelligence on how to visualize this Rashomon set. Although, to be honest, we have not actually done that for Ghost. So there is an important open problem there, which is how to do this for decision trees and for Ghost. We've done it for linear models, and we've done it for sort of sampling trees and so on, but not for really truly doing it for Ghost.
All right, thank you. Because I am also curious about what we can tell about all these generalization performances of these things that we are developing. I mean, you have been doing this for a far longer time than I just really jumped in this area. But the thing is, of course, there is this overfitting problem that we may face. And another thing is, I'm not really sure if I really run it with a different setting, then I will have really obtained. Probably the accuracy will be the same. The sparsity, if you can measure this, will be the same. But then it will be a completely different tree, and not necessarily tree, right? It could be also a bunch of rules. Then it's really hard to say which one is better. I'm getting confused there myself. That's why I asked that question. Thanks for the answer, though. Thanks.
Yeah, actually, people, it's funny because people ask that question a lot about trees, but they almost never ask it about linear models. But linear models are just as bad because if you have correlated features in linear models, then it could choose one or the other. And which one do you choose? And so somehow like linear models get away completely without people asking this question, but it actually pertains to all modeling classes and not just trees.
I don't think people really understand linear models that well. So I don't want to be cocky about this, but the thing is, then the weights will come out. But here, decision tree is very clear. And if you make a very small change, because they may not be very robust, and then you obtain a completely different tree, then they get confused. So there is, I think, this thing that they understand it so well, they can't just be cocky and say that they don't really trust it that much. Anyways, we can talk about this probably for
linear model. Yes, it's because you have two features that are correlated. You could use one has all the weight, and then the other could have all the weight. You make a tiny little change, and it shifts the weight completely from one to the other.
I agree. Anyways, thanks for the answer.
Thank you, Ilka, for the question, and thank you, Cynthia, for the answers. So we have another question from Emir Demirovic from TU Delft. Would you like to state your question, Emir?
Yes. Hello. So can you hear me?
Yes,
Hello.
we can
Great.
hear
You
you.
can also see me, maybe.
Not really.
Not really. Okay, well, maybe it'll turn up at some point. Okay, great. So thank you for this presentation and this work. So what I'm really curious about in this kind of setting, you have this sparsity coefficient. So you have this sparse objective, and you have to determine how much is a node worth in terms of your accuracy. So you have a coefficient for your sparsity. It's loss plus some coefficient times the number of nodes. So what I would just like to know in general, when you work with these kind of models, how do you determine that magic number? So what is the weight you put to every node? Do you try out different weights, or how do you do that?
So to be honest, I usually use 0.01 because that's a 1% trade-off. So in other words, I would sacrifice 1% accuracy to get one fewer leaf in the tree. And I usually don't adjust that. I usually just set it.
Okay, so you fix, so 1.1 means, so if
0.01.
So the loss function is, but the loss for accuracy is from 0 to 1.
Yep.
Okay, so it's like a tree with 10 nodes would have to have perfect classification, and then, okay, I see.
Yeah, well, it doesn't have to have perfect classification. It's just that I would sacrifice only 1% error to reduce the number of leaves by 1.
Okay.
Right, it's a trade-off between terms.
But wouldn't that be 10%? Because accuracy is from 0 to 1, and then if you put 0.1 on the nodes.
0.01.
Okay, I understand. Okay, great. Okay, so just to fix things. Okay. Okay, great. Thank you.
Sure. Yeah, that's the fact that the regularization parameter has an actual meaning is a major benefit to working with discrete problems.
Mm-hmm. Sure.
Thank you very much, Emir. And thank you very much, Cynthia, for the answer. Is there any other question in the audience? I wanted to to check two things with you because I know that you put your work in practice. So I think for the audience, it would be very nice if you tell us where you have implemented these trees or where you are planning to do, or yeah, it would be nice to.
So we haven't implemented Ghost on in terms of something that's gone into practice, but I have a project, long-standing project with a neurologist where we have implemented things in intensive care unit. He works with patients that are in intensive care in hospitals. These are critically ill patients at risk for brain seizures in their brain. And we have implemented scoring systems with them, but now we're trying to construct some treatment regimes, and so we're planning to use Ghost to try to help construct those treatment regimes. But the problem is not Ghost. The problem is the data is really, really complicated, and so that's what's slowing us down on that project. But that's what we plan to do.
Yeah, thank you so much, Cynthia. I think I stop myself and I go to Raphael, who would like to place a question? Rafael, would you like to?
Yes, hi. Can you hear me?
Yeah.
Yes, we do.
I have a quick question. It wasn't the slides. I was wondering what sample sizes this method has been tested on, but we went over the slide quite quickly. So what sizes of data sets can Ghost handle?
So the sizes, so I presented that very quickly. I kind of skipped it. So it was several thousand. The Compass data, I think, is like up to 7,000, I think. Sorry. Oh, no, I've skipped it. Yeah, so the thing is that the scalability and the number of samples is really not that interesting because since we're using bit vectors, we scale really, really well with the number of samples. The thing that none of these methods scale well on is the number of features. So if you handed a data set with, 100 data points and like 200 features, or a couple hundred data points and 200 features, a lot of these methods just choke.
Okay.
Right, because the scalability in features is like boom, whereas scalability in samples is much, much, much more gentle. So you see what I mean? Like these bit vector computations are so fast that you can technically just scale up to sort of very, very large sample sizes without suffering too much.
Okay, thank you.
Yeah,
Sure.
and I think I think Rafael, stated the question that I wanted to discuss. Yeah, scalability. Yeah, thank you for touching on that. Thank you so much, Rafael. I think there are 3 minutes left. If anybody else would like to state another question. I think you can see that your presentation was very, very popular with lots of questions, lots of interest.
They're all really good questions too, and some of the questioners are people who I'm like in awe of their work, and it's like an honor to sort of get these questions.
Yeah, we are very pleased. We are very pleased that we got such a well-informed audience. Okay, so don't know the name. I only know that the person has initials TEC. Would you like to state your question?
Yes. When you talked about lopping off subtrees that were equivalent, that's sort of like an anagram problem, in that one tree is an anagram of another tree. Do you have some super slick way of using the bit vector to determine that one tree is an anagram of another tree?
Yeah, so we have this data structure that stores all of the trees, like the partial trees that we've seen so far, and it's a very fast bit vector computation to determine whether or not the partial tree that we're currently working on is already in our, set of trees that we've already looked at.
So you're doing a fold on the remaining bits to the right of the current tree?
So that remember, each subproblem is represented by the data points that fit in it. So the subproblems are just sets of data points. It's just a single bit vector, right? It's like this data point, this data point, this data point, that data point fit in this subproblem. So I can compare this subproblem to the subproblem that's in the database very easily. It's just one simple bit vector dot product, essentially.
Oh, okay. All right, I think I've got that. Thank you.
It's not, I mean, it's not hard. It's not a difficult computation. And it saves a lot of time, which is great.
Thank you so much for your questions. We have Claes with another question, and I hope you can be brief. Sorry.
Yes, I'll be very brief. I hope you can hear me.
Yes,
Yeah.
we can.
Okay, perfect. I wonder if you tested the interpretability of such trees, of the end result, with some non-expert end users. For example, a doctor or health insurer?
So I want to say that there's a complicated answer to that question. So interpretability is very, very domain dependent. And so sparsity might not always be the right thing that you want for a particular domain. Sometimes it is, like for medical scoring systems, sparsity is what you want, but usually the doctors, like, to be honest, when we're working with doctors, we print out tons and tons of models and we let them pick one. or we let them tell us more constraints and then we redo the thing with the new constraints. So none of the, what I've presented here is mainly academic, right? We want sparsity, we want our loss function. But in reality, when we're working with a domain expert, we would really want to incorporate the constraints that domain expert wants in their own model. And that's not something that I presented today.
Thank you so much to both of you for the question and the answer. Yes, you can see that the trees and the interpretability topic, they have brought a very well-informed audience this afternoon in Europe, morning for you. And we thank you very much for your kind acceptance to present. And actually, we hope that you will be back soon and tell us about your new papers. Thank you.
Dolores.
And to the audience, thank you again for coming back this Monday. And yeah, we hope to see you next Monday with Victor Blanco. Thank you. Yes.